In the previous section on the normal distribution, we looked at the standard normal distribution with a mean of 0 and a standard deviation of 1, and we looked at how to solve questions like this, where you were trying to find the probability that z was less than a particular value. So here, with the mean of 0, the probability that z has a value less than the mean is 50%, and we looked at how we could use our calculator to find this. So the probability that our value of z was greater than 0.8. The inverse normal distribution essentially is the opposite way around. So this time we can see that we've been given the probability, and we know that the probability that z is less than a particular value is 0.877, and we're being asked to find that value. We saw in the previous video that the probability distribution function is actually very complicated, and therefore we can use our calculator, the probability distribution function, the normal distribution function, to generate that for us. And it's the same with the inverse normal distribution. So for instance, in this question, if you just have a look at the sketch intuitively, we can see that we know that the probability is 0.877. Given that the area under the entire curve is 1, we can see that we're looking at some value a of around about here. But how can we find out the exact value of a? Well, to do that, we can use the inverse normal distribution function on our calculator. So if you go to probability and then distributions and inverse normal distributions, this first number here then is the area to the left of any value. It's always to the left. So the area to the left of a particular value, which represents the probability. The mean is 0 and the standard deviation is 1. And that gives us a value here of 1.16, which looks about right approximately here. For part B though, we need to be careful because we are being told that the probability that z is greater than a is 0.2. So the probability we're being given is actually this one here. But remember, this value on our calculator on the inverse normal distribution function here has to be the area to the left. So it's much easier to think of this as, in fact, finding the probability that z is less than a when this area here is 0.8. These two graphs are analogous, but it just means we're less likely to make a mistake when we enter it into our calculator, because we remember that the area is the area to the left of this value. Mean is 0, the standard deviation is 1, which gives us a value of 0.842. Part C then, we're trying to find a value a such that the probability that z lies between plus and minus a is 0.42. So we're going to have to use some element of symmetry to find this out. Again, it's useful to start with a sketch. We know that this area here, the probability that z lies between these two values is 0.42. So because it's symmetrical, we can see that this area here is actually going to be 0.21. So this area here, this line's a little bit misleading, this area here then is going to be the difference between 0.5, which is this whole section here, and this section here, which is 0.21. So this is going to be 0.29. Similarly, this area here is going to be 0.29. So the way we can find out A is to say that we know, so this area here is going to be a half, and we've said this area here is going to be half of this, which is 0.21. So the probability that z is less than a is actually going to be everything to the left of this, which is 0.71. The mean is 0, the standard deviation is 1. If we substitute that into the function, we end up with an answer of 0.533. Given that x, the random variable x, is normally distributed with a mean of 15 and a standard deviation of 3, determine the value of x such that the probability that x takes a value smaller than x is 0.75. So this isn't normally distributed. Sorry, it isn't standard. It isn't the standard normal distribution z. We can still, however, calculate that using the inverse normal function on our calculator exactly the same way as we would have done here. The area to the left is 0.75. We can take that from the question. We know that the mean is 15 and the standard deviation is 3, and that gives us an answer of 17.0. Let's have a look at a more realistic question then. So this one asks, it tells us that cartons of juice are such that their volumes are normally distributed with a mean of 150 mils and a standard deviation of 5 mils. It tells us that 5% of cartons are rejected for containing too little juice. So just pause the video, have a go at that yourself. We've been asked then to cartons of juice, let's have a look at a more realistic real-world question now then. Cartons of juice are such that their volumes are normally distributed with a mean of 150 millilitres and a standard deviation of 5 mils. We're told that 5% of cartons are rejected for containing too little juice, so we're asked to find the minimum volume to the nearest milliliter that a carton must contain if it is to be accepted. So just pause that and have a go at that yourself. So for this one, again, start by drawing a sketch. We've got the mean of 150, and we know that 5% are rejected for containing too little juice. So we're looking at this value here, the minimum. So we've got, this is the volume, normally distributed with a mean of 150, and the standard deviation is 5. So this is what we're working with. We want to find the probability that V is less than M. So all we're going to do, the area to the left is 0.05, the mean, 150, and the standard deviation is 5. So we can just use our inverse normal function to calculate that to give us an answer of 142 millilitres to the nearest milliliter. Next question then asks us to look at potatoes. We're told sacks of potatoes with a mean weight 5 kilograms are packed by an automatic loader. In a test, it was found that 10% of bags were over 5.2 kilograms. Use this information to find the standard deviation of the process. So this one a little bit harder. Try and have a go yourself, and then we can go through it. Mass of the potatoes then is normally distributed with a mean of 5 kilograms and a standard deviation sigma. We're told that 10% of the bags were over 5.2 kilograms. So we know the probability that M is greater than 5.2 is 0.1. This isn't in the standard normal distribution, but we can actually use the same trick that we use when we look at the normal distribution to answer this by transforming it. So we can take the Z value. We want to find the probability that M is greater than 5.2. So let's take 5.2 and use the same formula we did when we we're looking at the normal distribution to convert that into a Z value. So the Z value is going to be 0.2 over sigma. And we therefore know that the probability that Z is greater than 0.2 over sigma is 0.1. But remember, we're interested in the area to the left. So we can think about it like this. The probability that this value Z is less than 0.2 over sigma, this is our value, equals 0.9. We can calculate that using our calculator, which gives us an answer of 1.281. However, that is this value here, 0.2 over sigma equals 1.28155. So in order to work out sigma, we're just going to take 0.2 and divide it by that answer, which gives us 0.156 to 3 significant figures. Quite a challenging question here to have a look at then just to finish. We've got a manufacturer who doesn't know the mean or the standard deviation of the diameters of ball bearings she is producing. However, a sieving system rejects all ball bearings larger than 2.4 centimeters and those under 1.8 centimeters in diameter. It's found that 8% of the ball bearings are rejected as too small and 5.5% as too big. What is the mean and the standard deviation of the ball bearings produced? So if you want, pause this, otherwise we'll have a look at this together. So we've got the diameter here, which is normally distributed with a mean, which we don't know, and a standard deviation, which we don't know. We do know, however, that the probability that the diameter is less than 1.8 centimeters is 8%, because we know that 8% are rejected as too small, and similarly the probability that D is greater than 2.4 is 5.5%, which are rejected for being too big. On the diagram then, this is effectively what we've got. The area to the left here is 0.08 and the area to the right here is 0.055. So again, we're going to need to standardize each of these before we can solve this. So the value on the left is going to be 1.8 minus mu over sigma. We still don't know what these are. We can do the same thing on the right here, and then we can actually calculate a value here. Ultimately, we're going to be using simultaneous equations. So the probability that this value z is less than this standardized value is going to be 0.08. So we can use our inverse normal function to find that. The area to the left is 0.8. It is now standardized, and that gives us a value here for negative 1.40507. So we've taken our standardized value, and that 1.8 minus mu over sigma equals negative 1.40. So this value in the standardized normal distribution equals that. Similarly, with the second equation, standardize the value, so 2.4 minus the mu over sigma. The value then, we can find this value, the probability that z is greater than this value, using the inverse normal distribution. Again, remembering here that we want to take the area to the left, which is 0.945, and that gives us a value of 1.59. So you can see that we've generated two expressions here, 1.8 minus mu over sigma, so that's the standardized value here. We can find that as negative 1.41, and similarly here we can find the standardized value, 2.4 minus mu over sigma equals 1.59. Two expressions with two unknowns we can solve using simultaneous equations to give us a mean of 2.08 and a standard deviation of 0.2.